The guidelines for finding limits at infinity for rational functions is something that we just kind of highlighted in the last two examples. I'll just kind of summarize them here. If you're finding the limits at infinity of a rational function, they can be entirely categorized by whether the highest power of x is in the numerator or the denominator, or whether it's equal. When the highest power is in the denominator, then the limit will always be 0, whether you're looking at the limit at positive infinity or negative infinity. If they have the same highest power in both numerator and denominator, then the limit at either of the infinities is the ratio of the leading coefficients. And if the degree of the numerator is greater, then the limit does not exist. It would be either a positive or a negative infinite limit. Let's take a look at example 4. This is a different style of function. So the guidelines and the shortcut that we talked about in the last view is not going to work on this one. But we still can resort to some of our limit theorems we saw earlier in this section. We want to show that the logistic function has different horizontal asymptotes to the left and to the right. Okay? Let's go ahead and find the limit as x approaches negative infinity first of 1 divided by 1 plus e to the negative x. We've seen a limit that involves e to the negative x before. Let's kind of go back and see what that limit was. So the limit that we had involving e to the negative x was when x was approaching infinity. We're looking right now at the limit as x approaches negative infinity, and that involved the function e to the x. The limit as x approaches negative infinity of e to the x is equal to 0. So what we can do that will make it a little bit easier is, if we wanted to, it'd be easier if we had a e to the x here. We can rewrite this, the limit as x approaches negative infinity, we can rewrite this as 1 divided by 1 plus 1 over e to the x. We get a complex fraction. Let's simplify this complex fraction. Multiply both numerator and denominator by e to the x. And this transformed it into the following. It's the limit as x approaches negative infinity. We're going to get an e to the x in the numerator, all divided by e to the x plus 1. And now we can use our limit theorem. When x approaches negative infinity, e to the x approaches 0. So this part's going to approach 0. This part too is also going to approach 0. And the other part is just a constant. So this limit is going to be 0 divided by 0 plus 1, which is equal to 0. So we do have a horizontal asymptote. As x approaches negative infinity, the graph of f of x would approach the value 0 in the limit. Now let's look at the limit as x approaches positive infinity of 1 divided by 1 plus e to the negative x. To this we can directly apply our limit theorem. We saw from the notes that as x approaches positive infinity, e to the negative x will approach 0. So directly this is set up so that this will approach 0. So overall our limit's going to be 1 divided by 1 plus 0, which will be equal to 1. And this is kind of a unique function. It's really kind of cool to see something like this. Anytime we were dealing with the rational functions, when they had limits at infinity, the limit from the left and from the right was always the same. Here, however, what we see is that this is an example of a function where the end behavior, the limit as x approaches negative infinity, that was one number, it was the value 0. But the limit as x approaches positive infinity is going to be equal to 1. Let's take a look at the next two. In example 5, they want us to find the limit as x approaches infinity of sine of x. We should all be familiar with the graph of sine, but the graph of sine is going to oscillate. As x approaches infinity, sine of x is not going to approach any real number. It's going to continually oscillate in between the values -1 and +1. So this would be an example of a limit that does not exist. So limit as x approaches infinity, sine x does not exist. And the reason is that oscillatory type behavior, it's not going to approach any one real number. Something that's closely related to it is the limit as x approaches infinity of sine x divided by x. If we wanted to kind of get a qualitative feel for what might happen here, you could certainly graph this. But if we think about what happens when x approaches infinity, sine of x, yes, it's true that it's going to be oscillating. So it's going to be oscillating between -1 and 1. Yet at the same time, while it's oscillating between those two fixed values, the denominator is going to get larger and larger and larger. So we would expect, perhaps, for the overall output to get smaller and smaller, and probably approach 0. Okay. So maybe a little bit of intuition. We might think or believe that this limit is going to be 0. The question is, how can we show this? Well, the limit theorem that we have from this section involves, things like constants over powers of x. They don't involve things with like a sine function. This is where our good old friend the squeeze theorem will come back in. We know this because -1 is less than or equal to sine x, which is less than or equal to +1. If I simply take this expression and divide everything by x, we see that sine x over x is bounded between -1 over x and +1 over x. And our limit theorem applies to each of those two pieces. The limit as x approaches positive infinity of 1 over x is going to be equal to 0, as to, well, the limit as x approaches positive infinity of 1 over x is also going to be equal to 0. So by the squeeze theorem, our function, limit as x approaches infinity of sine x over x, will also have a limit of 0.